The proposed research focuses on creating and observing a quasihole state in an optical lattice system using ultracold atoms. This setup aims to demonstrate the first controllable creation of a simple quasihole state in a condensed matter system, paving the way for observing anyonic statistics of quasiholes in a more complex system. The model used is the Hofstadter-Bose-Hubbard Hamiltonian, which includes complex hopping phases and on-site interactions, modified with pinning and harmonic confinement potentials. Exact diagonalization is employed to analyze the system's behavior under various parameters. Key quantities for detecting the quasihole state include the ratio between the mean square radii of clouds in the presence and absence of a repulsive potential, and density depletion created due to the pinning potential. Phase diagrams for these quantities over a wide range of parameters are provided as a guide for future experiments. This work builds upon previous studies on lattice systems with open boundaries and aims to overcome the limitations of defining filling fraction in small systems. In the realm of topological quantum states, the Aharonov-Bohm phase factor plays a pivotal role in understanding the behavior of charged particles in magnetic fields. Recent research has delved into the connection between this phase factor and density signatures, uncovering novel insights into the properties of Laughlin-type states. The study reveals a profound relationship between the mean square radius and the expected value of the total angular momentum, underscoring the importance of geometric constraints in shaping topological states. Furthermore, the ratio between lattice Laughlin and quasihole states emerges as a telling indicator of the lattice ground states, providing a valuable diagnostic tool for characterizing topological phases. The researchers employed a combination of analytical and numerical techniques to elucidate the intricate interplay between the Aharonov-Bohm phase factor, density signatures, and Laughlin-type states. By examining the density profiles and angular momentum distributions, they were able to discern distinct signatures of topological states, including the emergence of lattice ground states. The findings of this study have significant implications for the understanding and manipulation of topological quantum states, offering a new avenue for the exploration of exotic phenomena in condensed matter systems. The incompressibility of the Laughlin state is a crucial aspect of quantum Hall physics, with the quantity increment n representing the fractional density depletion of the quasihole. In systems with periodic boundary conditions, this quantity saturates at a certain value, indicating the fractional density depletion. However, in a finite-sized droplet, it gradually rises to a maximum value and then vanishes as the system size increases. This maximum value of increment n is taken as the density depletion and is used to generate phase diagrams. To explore this phenomenon further, numerical simulations were conducted for n equals 2 and n equals 3 particles, considering different parameters in the omega-5 plane. These simulations demonstrated a good agreement between lattice and continuum results for the maximum value of increment n, validating the numerical approach. Consequently, phase diagrams were constructed, highlighting regions conducive to the realization of the quasihole state. These findings have significant implications for understanding the behavior of quasihole states in quantum Hall systems, particularly in terms of their incompressibility and the role of system size. The results also underscore the importance of numerical simulations in elucidating the properties of these complex quantum states. The refined version starts directly with the content, maintaining a highly technical and professional tone. It covers all major points from the page, including the discussion on the overlaps between the system ground states and the ansatz states, the significance of the triangular region in panel B, and the site occupations for different parameters. Novel ideas, significant findings, and important arguments are highlighted throughout. The creation and observation of lattice fractional quantum Hall (FQH) states in ultracold atoms have been achieved through the utilization of a harmonic trap and a single-site pinning potential. The harmonic trap plays a crucial role in enabling the system to adjust its cloud size, allowing it to enter the FQH regime depending on the flux. This adjustment is critical for achieving the desired quantum state. Density measurements are essential for observing the quasihole state, which is a key characteristic of the FQH regime. These measurements provide insight into the system's behavior and can help identify the formation of the quasihole state. The text highlights the importance of identifying favorable regimes for creating the quasihole state. This includes optimizing the parameters such as the strength of the harmonic trap, the intensity of the single-site pinning potential, and the number of atoms involved. By carefully tuning these parameters, researchers can create conditions conducive to the formation of the quasihole state. In addition to density measurements, mean square radius and density depletion measurements serve as signatures of the quasihole state. These measurements offer additional tools for researchers to verify the existence and properties of the quasihole state. They provide valuable information about the spatial distribution of atoms within the system and how they interact with each other and the external potentials. Overall, the creation and observation of lattice FQH states in ultracold atoms represent a significant advancement in quantum physics research. The use of harmonic traps and single-site pinning potentials, along with precise measurements, has opened up new avenues for exploring complex quantum phenomena. Further studies on these systems could lead to a deeper understanding of quantum mechanics and potentially pave the way for innovative technologies. The authors of the research paper draw upon several studies to explore the concept of anyonic statistics in fractional Chern insulators. These include investigations into measurable signatures of bosonic fractional Chern insulator states and their fractional excitations in a quantum gas microscope, edge mode spectroscopy of fractional Chern insulators, real space probes for lattice quasiholes, time of flight measurements as a possible method to observe anyonic statistics, and fusion channels of non-abelian anyons from angular momentum and density profile measurements. Their work builds upon the anomalous quantum Hall effect, which exhibits an incompressible quantum fluid with fractionally charged excitations, as described by Laughlin in 1983. The supplementary material provides additional details on the separate mean square radius results with or without a pinning potential, the effect of the pinning potential strength, the energy gaps, and the three-particle results. Furthermore, the authors cite a study on the structure of the nearly degenerate manifold of lattice quasiholes on a torus, which is relevant to their research. Their work aims to advance the understanding of anyonic statistics in fractional Chern insulators, leveraging insights from previous studies to inform their methodology and analysis. In the supplemental material, the authors provide additional insights and results that complement the main text. They present separate results for the mean square radii in the absence and presence of pinning, contrasting with the ratio R, which is an indicator of Laughlin-type physics. Figure 1 displays these results, showing an inverse proportionality with the flux quanta per unit cell phi in regions of high overlap with ansatz states. However, this quantity also depends on the harmonic trap strength omega, making the use of the more robust quantity R a better reflection of Laughlin-type physics. The authors then investigate the effect of the pinning potential strength. For a given trap strength omega and flux quanta per unit cell phi, the pinning potential must be above a certain threshold to pin a quasihole. Figure 2 illustrates this, showing the maximum value of the depleted density in the off-plane. Comparing the results for different pinning potential strengths, V equals 2T and V equals 50T, the authors find that with increasing strength, the region of agreement with the expected value 0.505 becomes wider. Moreover, the authors examine the energy gap above the ground state for the same parameters. Figure 4 displays the energy gap, which becomes vanishingly small following the boundaries of sudden jumps in the overlaps. This can be related to a dramatic change in the topological character of the system across a boundary. The authors present results for 3 particles in a 13 by 13 lattice with hardcore interactions, examining the maximum density depletion delta n in the plane of harmonic trap strength omega and flux quanta per unit cell phi with varying pinning potential strengths V for n equals 2 particles. Figure 2 displays the maximum density depletion delta n for different pinning potential strengths V equals 2T and V equals 50T. For n equals 3 particles, calculations are performed for select points in the off-plane, as shown in Table I. The table includes the overlap OL between the system ground state and the Laughlin state, the overlap OQH with the quasihole state, the maximum density depletion delta n, and the ratio R between the mean square radii. The authors observe that when the overlaps with the Laughlin state and the quasihole state are both large, the ratio R is close to the ideally expected value Rydell equals n plus 1, equals 3 divided by 4 equals 0.75, and the maximum density depletion delta n approaches the ideal value, increment n. Ideal equals 0.571. Figure 3 showcases the overlap OL between the system ground state and the Laughlin state for n equals 2 particles with V equals 10T. The site occupations Ni, calculated for the parameters yielding the largest overlaps OL and OQH in Table I, exhibit the expected features of Laughlin and quasihole densities. The figure illustrates the energy gap, delta E, between the ground state and the first excited state of a two-particle system in a harmonic trap. This is depicted in the plane of the harmonic trap strength, omega, and flux quanta per unit cell, phi, for two different scenarios. One with no potential, V equals 0, and another with a potential of 10T, V equals 10T. In the context of the research, this energy gap is crucial for understanding the behavior of the system under varying conditions. The harmonic trap strength, omega, represents the confinement of the particles within the trap, while the flux quanta per unit cell, phi, is related to the magnetic field applied to the system. The energy gap delta E is a key parameter in quantum systems, as it determines the stability and the transition rates between different states. In this case, the gap is measured in units of T, which is a parameter that represents the tunneling rate between neighboring sites in the lattice. The figure shows that the energy gap changes significantly with variations in both the harmonic trap strength and the flux quanta per unit cell. For V equals 0, the energy gap is relatively small and varies smoothly with omega and phi. However, when a potential of 10T is introduced, the energy gap increases substantially, indicating a more stable system. This suggests that the presence of a potential can significantly alter the behavior of the system, particularly in terms of its stability and transition rates. This research is relevant to the study of quantum systems, particularly those involving ultracold atoms in optical lattices, where the interplay between the harmonic trap, magnetic fields, and potentials can lead to complex phenomena such as quantum phase transitions and topological states. The findings presented here contribute to our understanding of these systems and may have implications for future experiments and theoretical studies. The visualization in Figure 5 presents site occupations for three hardcore bosons in a 13 by 13 lattice, calculated for a harmonic trap strength of omega A squared, T equals 0.007 and flux quanta per unit cell of phi equals 0.125. The figure consists of two subplots, A and B, differing in the presence or absence of a pinning potential. In subplot A, without a pinning potential, the site occupations exhibit a characteristic pattern of peaks and valleys, indicating the formation of a vortex lattice due to the interplay between the harmonic trap and flux quanta. In contrast, subplot B shows the site occupations in the presence of a pinning potential, where V equals 10T. The pinning potential leads to a significant modification of the occupation pattern, with the emergence of localized density peaks at specific lattice sites, resulting from bosons being pinned to the lattice sites and suppressing vortex lattice formation. These patterns can be understood within the Bose-Hubbard model, where the Hamiltonian includes terms for kinetic energy, interaction energy, and the pinning potential. The strength of the pinning potential controls the degree of localization, with higher values resulting in more pronounced density peaks. These findings have significant implications for the study of bosonic systems in external potentials, highlighting the importance of considering the interplay between the trap, flux, and pinning potentials.